Hello students, welcome to today's session. Today we shall be discussing one important chapter of ionic equilibrium. In this chapter, there is a topic of buffer solution. Today I shall be taking up some questions of the type more than one choice. These are the questions which are sent to me in this last week by some student who are preparing for IIT Advanced. So they tend to become little apprehensive about this topic of buffer solution. So in today's problems, we shall be discussing by understanding of these problems, you are able to understand buffer solution in a much better way. So before I get on with the topic, let me share you what they basically have asked me. They said that they are being taught like this, that weak acid along with salt of conjugate base, or weak base along with salt of conjugate acid, or something, a salt of a weak acid weak base tend to behave like a buffer. The question they have asked, why such composition act as a buffer, that you have a weak acid along with its salt is acting as a buffer. They also have asked me that why weak acid cannot behave like buffer, in spite of the fact that whatever we are saying, that composition which is having a weak acid along with its salt, if this is a acid along with its salt is having a buffer type of a action showing, why not if we take only weak acid, because weak acid also would have its conjugate base, or this anion is also available in it. So all these questions is being asked to me, and the questions they have shared is, first question is this: which of the following composition act as buffer? This is the first question they have asked. Now if you would consider this question, because it seems to be simple question but it is engaging, if you are having a clear knowledge about the concept, then the question is very easy, otherwise you would not fetch the right answer. So make it a point, this particular question would have more than one choice. So if you would simply consider that this is a weak acid, if I consider it simply by this logic, that this is a weak acid, acetic acid, and along with this, so do you have a weak acid and a strong base. If you consider this viewpoint in your mind, then you would not reach to a right answer by just uh, taking an assumption that this sort of a scene should be there, then only it would act as a buffer, because weak acid and NaOH would react with each other. So make it a point that you have not to literally take a meaning that you need to see in a composition, like say this is weak base but it is strong acid, and here you have a strong acid and this is a salt of conjugate base. So all of these problems, keeping aside the last one, pyridine is a weak base and this is a salt, here you can see that this composition is directly, you can say with that particular definition, that you have a weak base and it's salt. Now does this mean that others are not acting as a buffer? So for that understanding, I am first explaining you in another 5-7 minutes what exactly is buffer, how does it work, and you would really get to know what exactly do we mean by buffer. So let me start. So buffer solution is what? It's a solution which tend to resist the change in pH. Let me mark this as which tend to resist the change in pH. Now how? It is going to resist the change in pH if you add small amount of acid or base. If you add small amount of acid or base to any solution, the pH is bound to change. But if that composition is showing buffer action, on addition of some amount of acid or base, the pH would not substantially change. When it is not substantially changing, we shall be saying it is acting as a buffer. Say for example, if I take example of blood, in blood is having a buffer composition, and in a day we are eating so many things of alkaline, acidic, number of different type of entities we are eating which is having different pH, but the pH of our blood generally doesn't change because it is having some buffer composition. And another thing, that if into buffer solution, if you add water or dilute it, its pH would not be changing much. So this first is the fact. This is also being asked to me, that is addition of acid or base to a buffer changes the pH? Yes. But if the change is invariably very less, we will say then that particular solution is showing good amount of buffer action. Now let me understand what do we mean by buffer then. Buffer is, you can take if I have to explain the conceptual understanding of this point, that what do I mean by buffer, first let me explain it like this. Say for example, I have taken three cups, A, B, C, three solutions, and in the first one there is a pure water. So if it is a pure water, we will say its pH is 7 at to begin with. And here I have taken acetic acid along with its salt. Acetic acid along with sodium acetate, two entities are added into it such that the composition becomes 5,5 molar. 5,5 molar. Here also I have taken acetic acid along with sodium acetate. Here it is, the concentration is lesser but equal. Here also the concentration is high but equal. Now into this particular solution, if I happen to say that in these three cups, if I would have added, say for example, 10 raised to power minus 2 moles of HCl gas as a simple statement. So I dissolve this HCl gas into it, because HCl is a strong electrolyte, as and when you put this particular gas into water, it fully ionizes. I added into these three solutions same amount of HCl. Now what would be the fate of addition of this HCl? Before going into that, I shall also mention that the pH of this particular solution is around 4.74, and pH of this also is 4.74, and that do make a sense also. As I said, if you dilute the buffer solution, keeping the concentration equal, then of acetic acid and sodium acetate, the pH would not be changing. So buffer, this again endorsing the point that it is showing the buffer action. Now another thing, now into this, both the solutions, into three solutions, I added 10 raised to 2 moles of HCl. So what would happen? The as soon as this H positive HCl comes into it, it ionizes to form, this is 10 raised to minus 2, because you added 10 raised to minus 2 moles. So this 10 raised to minus 2 moles is added into 1 liter of water. So basically it becomes molarity, and the pH is equal to minus log H ions. So this would become minus log 10 raised to power minus 2. So the pH turned out to be 2. So the pH final I would get equal to 2. So what is the change in pH? The pH got changed by 5. pH got changed by 5 units. So we shall be getting here 5 unit change. The pH got changed from 7 to 2. If I added 10 raised to minus 2 moles of HCl into the water, the pH got changed by 5 units. Now, same amount of HCl, if is being added to here, the final pH here would come out to be 4.74 minus 0.0018. So the change in pH is very small. So the change in pH is 0.0018. And for that matter, how do I get it? I will explain it in minutes time. The pH final in this case happens to come out to be, this was the initial and it got decreased by this much entity. Almost the change in pH is of the order of 0.18. So this is what we have added, because you added HCl into the system, the pH is bound to change. But what we have seen, that the pH change in the case of cup B is substantially less. It is invariably very, very small. So the magnitude of change in pH in this case is of the term this much units, and in this case it is approximately 0.18, the changes of this much unit. So what we are going to say, that on vis-a-vis basis, that had I added 10 raised to power minus 2 moles of HCl into pure water, the pH dropped from 7 to 2, 5 unit change, versus if I have added it into acetic acid sodium acetate having concentration 5,5 molar, the change in pH is practically ignorable, because this change in pH cannot be detected by pH meter. If the pH meter is highly sensitive, then it is going to tell us, otherwise it would show almost same pH. So which solution among these is showing the best buffer action? We will say B is showing the best buffer action. Also, because you have just understood it, and also make it a point, when the concentration of acetic acid and sodium acetate are equal, that is 5,5 molar, and high, when the concentration of buffering component, I'm going to explain what is buffering component, when the concentration of acetic acid and sodium acetate is equal and high, then it would show best buffer action. So the concentration of buffering components should be equal and high to get the best buffer action. Now, how do I get this pH? That is also a point to understand. Now, let me explain it in another way, that how does this buffer has actually worked, why the pH drop in the case of second cup is very small. The reason for that is, let me explain it this way. Now all of you are aware of that acetic acid is a weak acid and this is containing its conjugate base, and Ka for this reaction is almost 10 raised to a minus 5. So it is weak electrolyte, so it is not going to give you high value of Ka. But if I reverse this reaction, so what I shall be getting, the Ka minus 1 would have the value of the order of 10 raised to a 5. So reverse way it is highly favorable. But if you go from this side to this, it is not advisable because it is not going to dissociate much. But reverse way it is very, very fast to get the acetic acid. Now the fact of the matter is, now how do I explain what exactly, why in the second case the buffer action was very effective, why the pH has not dropped much. Now try to understand, this is again a very interesting point. So say for example, I have taken again acetic acid just to make the things easier and speedy, and sodium acetate. And into this, let's say I added, say for example, here you have 10 moles of it, and here also you have 10 moles of it. And into this you added 5 moles of H positive, and that H positive may say come from the HCl. So you added 5 moles of, now in this solution two entities are there, sodium acetate and acetic acid, and into that you added 5 moles of H positive. Now first let us understand what would be the fate of this H positive when it is being put into this type of a composition. So H positive would definitely look for a basic species because it itself is an acid. So it would look for acetate ion. That is very beautiful. It would look for acetate ion. And how many acetate ions do I have here? Almost 10 mole. And as I just have spoken about, this acetate ion would act as a strong base because this equilibrium constant is very high. This would rush to the forward direction like anything. So this would go very speedily to the forward direction. Almost it is 100% goes to the product side. So what exactly do I get here is that I added 5 moles of it, and 5 moles of it are immediately depleted. Very rapidly it got depleted, and it, the acetic acid already I have 10 mole and 5 new moles have been added, so it becomes 15 mole. Did you get it? Now the point is that what you added, this H positive you added, this is the H positive we added, this H positive got depleted speedily because of the fact that the solution is containing some acetate ions, and that too in good amount of quantity. So the, now here I can explain why weak acid cannot act as a simple weak acid cannot act as an what you call it as a buffer, because the weak acid in itself would contain very less amount of acetate ions. It would contain very less amount of acetate ions. If it contains very less amount of acetate ions, it is going to neutralize very less number of H positive which is externally added. So that is the point why we generally add along with weak acid a strong electrolyte in good quantity, so that if you have added acid, it got completely consumed up very speedily. Now another thing, so this is the reaction number 1. This reaction number 1 has very high Ka value. This value is very high, and that is why it has driven forward. Now what would be the fate of this new acetic acid which is being generated? Let us understand that one also. The acetic acid which just we have made now would break once again into this part. Now what would happen? The Ka for this is very less. It is very less. The Ka value for this is 10 raised to minus 5, and for this it is 10 raised to 5. So here what would happen? This what 5 moles which we have got from the previous, and in total you have 15 moles, but I am just concentrating on the fact the new acetic acid which we have formed, these 5 moles of acetic acid I actually made from the H positive, 5 moles of H positive which has been added to this solution. So these 5 moles of acetic acid now would dissociate to a very less extent because this is already present in the solution. This acetate ion would not allow this acetic acid to undergo dissociation further because of the common ion effect. So this equilibrium would not be driven forward. So what I am saying here is the 5 moles of acetic acid definitely would give some H positive here, the quantity of H positive would be very, very less because this is the left out moles. The acetate ions are already there in the solution, which would not allow this acetic acid to undergo dissociation further. So what we are going to say is that there are always in a buffer action two reactions happening. First reaction would consume the added acid or base very rapidly. As a consequence of that, if you have added an acid, a new acid is being generated. That new acid would dissociate to a very less extent. What I am again endorsing the fact that the 5 moles of H positive which I have added, that only gave me very, very less amount of H positive, very less amount of H positive I actually received into the solution because of these two reactions. First reaction is rapidly going forward, and second reaction is partially dissociative. So fact of the matter is there are two reactions happening. For first reaction rapidly goes forward, and second reaction is not going very speedily to the forward direction. As a consequence of that, you are not getting same number of H positive ions which you have added as is in the case of water in this particular solution. Same analogy you can take for the addition of base. Had you added 5 moles of OH negative into this solution, so this OH negative would have reacted with acetic acid, and acetic acid was 10 moles and you added 5 moles of it. As a consequence, you get sodium acetate or acetate ion along with water, because this is acting as an base and this is an acid, and acid base reaction goes to completion. And this, as a consequence of this 5 moles got totally depleted and this 5 is left out, and already I have here acetate ions as 10 moles and this 5 are newly generated. Now this 5 newly generated acetate ions would hydrolyze to a very less extent. This would react with water to form acetic acid plus OH negative. And this, the KH, this is called as hydrolysis constant of this anion. KH of this KH is of the order of almost 10 raised power, almost you can say 10 raised power minus, you can take around 9, so or 8, 10 raised to a minus 8 or minus 9. In this range the KH value of acetate ion is there. So what does it mean? Now if you see this reaction in a reverse way, this reaction is very speedily forward driven because KAH1, because if I do the reverse of this reaction you would get this reaction. So KH negative, KH minus 1 is very high and KH is very low. So what basically we happen to say that the OH negative, 5 moles of OH negative which you have added, actually we did not get that much number of OH negative. So this is what you call it as buffer action. Now I think the things would be clear. Now one more thing, what is buffering component? A buffering component in any buffer is the weak acid along with its salt. Along with its salt. These two are the requirement because both of these are required in two steps. One step where the H negative or OH negative is speedily consumed up. See here, if you have added OH negative, why does it got speedily consumed up? Because you have sufficient amount of acetic acid. And in the second step, this acetate ion will then hydrolyze to form the acetic acid. So the point is that you shall be requiring two components, one acetic acid and second is sodium acetate, or for that matter, if you have ammonium hydroxide along with its salt as ammonium chloride, or this is a weak base and this is a salt of conjugate acid. Now the mathematical understanding of this particular concept, you can figure it out like this. This is a weak acid and this is a conjugate base. So these are in equilibrium, but we have added this salt from externally. This salt is added externally also, so that we could have high concentration of acetate ions and acetic acid. Because if the salt is added externally in a large quantity, this equilibrium goes backward, and in that sense we have good amount, high concentration of acetic acid as unionized, and also would have acetate ions or carboxylate ions along with coming from the salt. Now if I write the Ka for this value, for this equilibrium, so the H ions, if I rearrange this equation, you would get this one. If you take minus log of both equations, so you would get minus log H positive minus log Ka and this term, and this rolls down to pH, and this is pKa, because minus log H ions is pH and minus log Ka is pKa. And this negative sign, if I make it positive, this undergoes reciprocation. So you happen to get this equation. So this is the equation to get the pH of a buffer, and this is called as Henderson-Hasselbalch equation. This is called as Henderson-Hasselbalch equation of buffer. And similarly, you can get the same entity for the base also. For base, if you have a basic solution, you could get the same feel that way. So you end up getting the same thing in the basic buffer also. If you have a weak base, if you have this as to be the weak base, along with that salt, this is the salt which is externally added. Salt is externally added into this composition, and similarly Kb, and rearrange this equation. So this again would give you POH, that is POH is equal to pKb plus log salt upon base. Now coming on to that particular question, now we have to figure it out which out of this would act as buffer. So we have understood one fact for sure, that any composition would act as buffer if into that you add acid or base. First, that acid or base is completely consumed up very speedily, and new acid or new base is being formed which dissociate to a very less extent. As simple as that. Now let me check what are the compositions available. Now if you would see this from this standpoint of view, that it is a weak acid and this is a strong base, so it would not be acting as a buffer. No, these two would definitely react with each other. Weak acid and strong base would react to form sodium acetate along with water. Now here what you have, this is having a 10 millimoles, this is having a 5 millimoles, because molarity and volume gives you, if volume is in milliliters, gives you millimoles. So what would happen? 5 moles of this would react, because this is acting as a LR. In this case, it is acting as a limiting reagent, because the 5 moles got completely consumed up and you are left with this 5 millimoles are left out. And along with it, you also would get 5 millimoles of sodium acetate. 5 millimoles of sodium acetate you got. So now you are able to see that you in this composition you have acetic acid along with that salt, and how much of these are there? 5 millimoles of this and 5 millimoles of this. So this would act as a buffer. This composition would make a solution buffer. At this point of time, if you have added 50 ml of 0.1 molar NaOH into this particular acetic acid 100 ml 0.1 molar, this would show buffer action. If you add acid or base into it, it would not change pH to a much extent. Similarly, if you consider this as to be weak base, this has to be strong acid, but both of these are going to react, and once they react, you would get ammonium chloride plus water. Now, what shall I be writing here? So 6 millimoles of this would react with 3 moles, and this got completely consumed up, and this 3 millimoles are left out. And what is being generated? 3 millimoles of ammonium chloride are being formed. So again, you would get a weak base along with that salt is present in the solution also. So this also would act as a buffer. So this also is a very important question. Now the C option is very interesting to figure it out. So C option is very tricky also. Now what is being given to you? You are being given a strong acid, along with it you are being given a salt of conjugate base. This is the main question they also the students have asked in this particular question. So this also is a very interesting question to discuss. Now HCl would give me H positive, and sodium acetate is a very strong electrolyte. When you put this into water, it would give you good amount of acetate ions. So what would happen? This acetate ion definitely would react with H positive to give you acetic acid along with NaCl. Now you would also see there is 20 millimoles of this and 40 millimoles of this as per the composition. So 20 got reacted, this becomes 0, and this is minus 20. So your 20 millimoles are left out, and along with it you would also get 20 millimoles of acetic acid. 20 millimoles of acetic acid. So again, what you are able to see, that in this composition HCl is acting as a LR, it got completely consumed up, and you are left with sodium acetate and acetic acid. This is the very definition of buffer which we have just spoken in today's session, that weak acid along with its salt may act as buffer. So 20 millimoles are there, so it would also act as a buffer. And last option, that also is very interesting. That is a bit simple, but here why the students have got little confused up, because pyridine is this much, this C5H5, and this is pyridine. Pyridine is a nitrogen containing base or nitrogenous base. So basically, in the case of nitrogen containing base, say for example this one, or you are given some primary amine or secondary amine, so there what you have to, my suggestion would be, always when you get something where the nitrogen is containing any amine type of a species, just treat that as to be ammonia or ammonium hydroxide. This is tip to remember from my side. Treat that nitrogen containing compound as ammonia or ammonium hydroxide, whichever way you want to say, and that actually is a weak base. And ammonia would have ammonium chloride at its conjugate base, or ammonium hydroxide would have ammonium ion as its conjugate base. So this pyridine is a weak base, and it is having a salt along with it, and 22 millimoles are there, so it again would act as a buffer. So in this particular question, we shall be saying all the options are acting as buffer. So I think what you people have asked, I'm able to do the justice to this particular question. So all of these would act as A, B, C, D. All of these options would act as buffer. So I think the statement is clear. Now going on to the second question, which also is a very tricky and important question. In that particular question, we are being asked, let me show it to you. What is basically asked in this particular question is this thing: which among the following composition is or are suited to give a buffer action around pH 4? So you are being asked that among these options, 4 options, and you are being given pK value of acetic acid and formic acid. So what is being asked now? First you have to check that which of these composition would give you a buffer solution of around pH 4. So acetic acid, so potassium acetate or salt is being given, acetic formic acid and its salt is given, acetic acid along with sodium acetate, and formic acid along with its all the 4 option is containing weak acid along with salt. So what is the formula for the pH for this? So pH would be pKa plus log salt upon acid. Salt upon acid. This is what you are supposed to do. And concentration of salt upon concentration of acid. Now what basically I can do here is that if I place all these values in this options, so this is 100 ml, and because what I'm going to do, this is again very important to tell you, when you mix them together, let me show it here only. When you mix them together, let me show you the first option first, that 100 ml of this and 50 ml of this. So the total solution would become 150 ml. And the formic acid which I just have mixed, formic acid which I have taken, so it is how much? 100 ml into 0.5 molar. So this is the millimoles which I have added into it, isn't it? I added 50 millimoles, and 50 millimoles of this acetic acid is being added to 50 ml of potassium formate. So that means the total solution, if I have to write the concentration of formic acid which I got into the solution, would be 50 millimoles upon 150 ml. So milli got cancelled, so you get 50 upon 150 moles per liter. And similarly, if you see into this, what is the composition of potassium formate here? So potassium, because we have to find the concentration of salt also in the solution. So what we shall be writing, what is the salt? Salt is 0.1 molar and it is 50 ml. So that means you have added 5 millimoles of potassium formate into solution, and the solution now would become 150 ml because 100 ml is there only. So we shall be saying what is the composition of this, what is the concentration of this salt? It is 5 millimoles which we have added, but the total volume becomes 150 ml. So milli again got cancelled. Now the important point, basically when you add them together, the final volume for salt and acid would always be same in a buffer equation. When you mix them together, because salt and acid both are present in the total volume, so number of moles of salt upon volume upon number of moles of acid upon its volume, this volume got cancelled. So that is why on addition of water also, the number of moles of salt and acid is not changing, and volume got cancelled, so you would end up getting the same pH. So that is why I have done it this way, that just divide the moles. If you divide the moles in all of these options, the volume term got cancelled. So this is 3.7, pH is pK is given to us. So what is the composition of salt? 100, where it is written, it is salt upon acid. So salt upon acid, if I take it, this is 50 ml, I think so. This is 50 ml. It is misprint here. 50 into zero point 0.1. So this is 50 into zero point 0.1, and this is 100 into zero point 0.5. So this rushed down to 2.7. And second option is 100 ml 0.1 molar. This is the salt divided by 100 into zero point 0.5. This is being done here. So log 5 is almost 0.669991. So I just take zero point 0.7. So this gives you 4. And similarly for the other ones also. Now the important point here is that in the solution in the option B and C, the pH comes close to 4. So in this particular question, answer to this question would be either of B or D option. These two options are giving you the pH close to 4. Now, last very important statement, I'm going to discuss it with you. If in case this had been a single choice question, in if it had been a single choice question, I would have asked you this way, that which among the four solution is showing best buffer action at pH 4, best buffer action at pH 4. Then your answer shall be either you would say 4 of the B option or D option. But I'm asking you, out of B and D, which is the best one? Out of B and D, the best one is which would have more number of moles of buffering components. The one which is having, let me show it here, best buffer action is seen when the concentration of acid and is equal to the concentration of its salt, and both concentrations are high. When the concentration is high and equal, it generally would show best buffer action. But here what I am able to see here in the B option, you have how many moles? This is having a 50 millimoles of acetic acid and 10 millimoles of sodium acetate. Vis-a-vis, here you are having uh, almost point this is 100 millimoles of formic acid, and here you have 50 ml of potassium formate. So here in this problem, we shall be saying that the number of millimoles of formic acid and number of millimoles of potassium formate are more and more closer to each other in terms of concentration as compared to in the B option. So best among these four options would be the D option. But as for this particular question, we shall be saying the answer to this question would be B or D, with one correction here, that it is 50 ml because it is being written 50 here, and one more correction in this, it is 0.2, which is digitized wrong. This is 0.2 and this is 0.1 as a simple correction here. So thanks a lot. I hope you have understood what we actually meant by the buffer action. Let me consolidate. Buffer solution or buffer composition is the one which tend to resist the change in pH. How does it do? When you add acid or base into it, that composition has something in it that it consume that added acid or base very rapidly and generate a new acid or new base into it, and that would dissociate to a very less extent. And secondly, when the composition is such that the acid and its conjugate base salt, or weak base and its salt is having a concentration equal and high, that particular composition would give you very good buffer action. Thanks a lot. Have a nice day. Stay safe. And do let me know if you are liking my content. Do subscribe to my channel and share it with your friends. Thanks a lot. Have a nice day. Stay safe and take good care of yourself.